we've looked at various gas laws. We've looked at Boyle's law, Charles' law, Gay-Lussac's law, and the ideal gas law. Each of these laws describe what relationship we observe between various properties, whether it be pressure and temperature and volume, temperature and volume. And so now what we want to do is we want to look at how do we explain why each of those laws are valid. And that's where the kinetic molecular theory comes into play. Remember, a theory is explaining why we observe certain laws. And so, like Dalton's atomic theory, the kinetic molecular theory has various postulates. Okay, and so those postulates are, first off, gas particles are comprised of a bunch of teeny particles, and they're moving in rapid and random motion. So there's no rhyme or reason, they're just always moving around within a container. Secondarily, the volume of those gas particles is negligible compared to the volume they're occupying. So what that's saying is if I were to take all those gas particles and condense them down touching each other, it would be negligible compared to the total volume that they exist in. Third, is that it's saying is that when these particles collide with each other, they're perfectly elastic collisions, meaning energy is not lost in those collisions, and they move in direct straight lines in between those collisions. So those are kind of the three postulates that we can use to try and explain Gay-Lussac's law. So we're going to use that example here of Gay-Lussac's law. Okay, so Gay-Lussac's law is the pressure-temperature relationship. Okay, so Gay-Lussac's law seeks to show that pressure and temperature are related to each other. Now again, this was a fixed amount of gas at a fixed volume. Okay, so this is what we're going to do here. Let's say we have a container, and inside that container we have some gas particles, right? So we have these gas particles inside of our container. Now one of the postulates here says the volume of these gas particles, number 2, is negligible compared to the total volume that they're occupied in. Okay, so that means that they don't really contribute to the total volume of this container. Just the fact that they're really far apart from each other. This is at a specific pressure called P1 and a specific temperature, T1. So all of these particles are moving around in random motion. Okay, so they're all moving around and they're colliding with the wall, which is exerting a pressure. Okay, well, they're all moving around in this random motion. And so we can see for sure that's why we have a pressure. They're all moving around and colliding with the walls of this container. So one important thing here we'll see is that the pressure is directly proportional to the number of collisions between the gas particle and our wall here. Right? So the more collisions we have, the higher the pressure would be. The lower the collisions, the lower the pressure. And again, this has to be per some unit of area. So we'd have to look at some unit of area. Well, if it's a fixed area, then we would think of just the number of collisions. So now what we would do is let's go ahead and increase our temperature. So again, we have our container here with the same volume, and we have same number of particles. We haven't changed the number of particles. So now if I increase the temperature, the kinetic molecular theory, kind of abiding with these postulates, says that an increase in temperature increases our average kinetic energy. So if we increase the average kinetic energy, what does that mean for our particles? That increase in average kinetic energy means we have an increase in our average velocity. So these particles are moving faster on average. And so now that we've increased the number of collisions with the wall because our particles are moving faster, they're all moving around. Some are moving really fast, some are moving a little bit. But on average, they're all moving much faster. So as we've increased temperature, what we'll see is that we have a higher average velocity of all of our particles. What that means is that we are going to have more collisions with the wall of the container. Since we have more collisions with the wall of the container, that would tell us that our pressure would be higher. Right? We would see our pressure gets higher as we have more and more collisions with the wall of our container. And so now what we've done is we've explained why we see an increase in pressure with an increase in temperature. Right? And we've used these postulates of the kinetic molecular theory. Right? They're all moving in this kind of random motion, and these particles are all kind of random in how they're moving, and there's perfectly elastic collisions. We're not losing energy as they collide with the wall, but as we increase the temperature, they're all moving faster and they're colliding with the walls more often, and what that does is that increases our pressure. And so we could see we could do the same thing to explain Charles' law. We can do the same thing to explain Boyle's law. We can do the same thing to explain Dalton's law of partial pressures. So we see that we can use the kinetic molecular theory to explain each one of these. And so we're going to unravel these more and more in class and thinking about, well, what about the other gas laws? Can I explain why Dalton's law of partial pressures makes sense? Why does it make sense? Why is Charles' law valid? And we're going to do that by explaining them through the kinetic molecular theory.